in this screencast some results about Euclidean inversions in circles that matter. Some lines become circles under Euclidean inversions. Here is a circle centered at O. Here is a line L. This line has some point P on it. We know that P prime has to be inside the circle. We know that. It's some point right about here. And we're going to pretend that P is the foot of the perpendicular. We're just going to make P the foot of the perpendicular from O to the line L. If you pick any other point on the line, the image of that point has to be inside the circle, right? The image of the point has to be inside the circle, right about there. But because angle OPQ is a right angle, and triangle OPQ is similar to triangle OQ prime P prime, then angle OQ prime P prime is a right angle. And if that's a right angle, it is inscribed on the diameter of a circle. That means that OP prime is the diameter of a circle. You'd never know it from my diagram. Gosh, that's hideous. OP prime is a diameter of a circle containing Q prime. And so for every one of these points, we get a point on this red circle. Lines become circles under Euclidean inversions. But not all lines become circles. Clearly, lines that go through O remain as they are. You take any point P, its image P prime is on ray OP. Ray OP passes through O, so ray OP prime passes through O, so the line stays the line. Lines that pass through O remain lines that pass through O. And circles that don't contain point O remain circles that don't contain O. The images here, so you get a circle that doesn't contain O. Here's the rough idea. We take the diameter QR of this circle here, and we take this point P here, so that if we construct this ray and we don't draw the picture terribly, P prime ends up out here, Q prime over here, R prime over here. It can be shown without too much trouble that angle RPQ is congruent to angle R prime Q prime, R prime P prime Q prime. It can be shown. You're going to do that with angle sums and similar triangles, and you're gonna play with that for a little bit. But it can be shown that angle RPQ is congruent to angle R prime P prime Q prime, which means that if this one is a right angle and therefore that's a right angle inscribed on a diameter giving us a circle, then the same thing has to happen out here. So circles that don't contain point O remain circles after the inversion. Here's the curious thing. The curious thing is, if we have a circle that comes through in a special way. If this circle is orthogonal to our circle of inversion, if the tangents here are perpendicular and the tangents here are perpendicular. So the green circle is orthogonal to the circle of inversion. Tangents here are perpendicular, tangents here are perpendicular. If this circle beta is orthogonal to the circle of inversion, then the image of beta is in fact beta. And you can prove this. I'd encourage you to do it. But all of these points have images that are out here and vice versa. The red arc becomes the blue arc becomes the red arc. It's not terribly difficult to prove, and it does hinge on the orthogonality of the green circle with the black circle. It does not hold. This result does not hold if the green circle is not orthogonal to the black circle. But if it is, if those circles are orthogonal, then the image of the green circle under an inversion in the black circle is the green circle, but the inside becomes the outside and the outside becomes the inside. I should note, because this matters, that this orthogonal circle is unique. So you give me any 2 points, R and S. There is one and only one orthogonal circle to the black circle passing through R and S. How do we find it? We construct ray OS, we figure out where S prime is, and then there is one and only one circle passing through S prime, S, and R. We do that by taking triangle RS, S prime, and finding the perpendicular bisectors of the three sides. Those are concurrent in Euclidean geometry at the center of a circle that passes through RS and S prime. So by finding the image of one of the points under an inversion, we get an orthogonal circle to the circle of inversion passing through R and S. So that's a pretty neat result. It's a pretty neat result. It is something that we appreciate and that has an effect on the last thing we're going to do in our course. So these are some results that are important to keep in mind for Euclidean inversions, and that's all I have to say.